Hi viewers, this is Sri Ramulu, DL in Physics, DL lecturer in Physics. My YouTube channel name is yes.yes space physics. So friends, don't forget subscribing this channel. And today's is very important topic is I brought, and this topic not only useful here and also in the low temperature physics. So that is why please listen again and again this video, and is somewhat it is lengthiest. Okay friends, so this is very important topic. Today's topic is that is a Joule Kelvin effect. Okay, what is Joule Kelvin effect? When a gas under a constant high pressure is passed through a porous plug to a region of constant low pressure, there is a change in its temperature. This is called as Joule Kelvin or Joule Thomson effect. Okay, so either Joule Kelvin we call it is or Joule Thomson. Okay friends, when a gas under a constant high pressure, for example, let it is a device like this. Let here it is a walls like this, and here I kept one sheet iron sheet, and before that let me make a small holes to the iron sheets of both sheets, and fill this gap with either cotton or silk or any other material which has small holes, and keep this side one piston, fix this side one piston, and this side also one piston. Okay, and let this side is a high, this filled with gas, and let this also filled with gas, but difference is what, let it is at higher pressure and it is at lower pressure. That is the main difference. Now if you apply the force on this piston, then piston starts to move in this direction and it compresses the gas. Okay, so that means the work is done on the gas. Here piston is forcing the gas, so that means it is work done on the gas. Then what happens, this gap start escaping through the small holes. These small holes are called pores, porous or pores. Pores also we call, not only porous, and pores also we call. Pores means small holes, or bores also we call, bores. Then these gas travel through these porous plug and enter into the low pressure region. Then what happens, change in temperature will occur. Change in temperature means what, sometime temperature increases and sometime temperature decreases. That is why I'm saying change in temperature. So change in temperature will occur like this. Okay, this effect is observed by the Joule Kelvin and or Joule Thomson. So that is why this is called as Joule Kelvin effect. Okay, now through this experiment following points are observed. What, all the gases when passed to the porous plug suffers a change in temperature. Okay, at ordinary temperatures all gases except hydrogen and helium suffers fall in temperature. Okay, at ordinary temperature means room temperature, all the gases suffers fall in temperature, but not hydrogen and helium. So gas which suffers fall in temperature, that is called cooling effect. And while hydrogen and helium suffers a slight rise in temperature, is called heating effect. Okay, at a room temperature, at ordinary temperature, helium and hydrogen, it's at their temperature increases, but other gases temperature decreases. So that is why that is decreasing in temperature is called cooling effect, increasing temperature is called heating effect. Change in temperature is directly proportional to the pressure difference on two sides of the plug. Okay, so change in temperature depends on what, pressure of high region and pressure of low region difference only. They difference to their difference, the fall in temperature depends. As the initial temperature of gas rises, cooling effect diminishes, right? Cooling effect decreases. Okay, when initial temperature rises at a certain certain initial temperature known as inversion temperature, cooling effect is changed into heating effect, right? When cooling effect is converted into heating effect, then at a particular temperature, what happens? Cooling effect is converted into heating effect at a particular temperature. This particular temperature is called inversion temperature. Okay, so now expression for Joule Kelvin coefficient. What is the expression for Joule Kelvin coefficient? When a gas suffers Joule Kelvin effect, total enthalpy of gas remains constant. Okay, when a gas suffers Joule Kelvin effect means a gas undergoes Joule Kelvin effect, then their enthalpy is always constant. So enthalpy H is equals to U plus PV is always constant, means H is constant. And a differentiation of H is what? 0. So that is why it is made to 0. And it's a differential D. So multiply D value inside du plus D of PV. Now it is make it as UV method. PdV plus VdP. UV. It's a UV method. Okay. But we know that already du is change in internal energy written as TdS minus PdV. Okay, TdS minus PdV. Now PdV cancel. TdS plus VdP we got here. Now let me change entropy. This entropy. For this, what I am doing? Let us suppose that S is a function of P and a T. Then change in entropy ds can be expressed as. So likewise equation already I explained uh, in what, in a ratio and difference up to specific heats. There I explained how do we have to differentiate. Once again let me explain. So it's a differentiation. Let me write ds. Okay, it is also function of S only. So ds, I am writing ds as dou s by dou p into dp. If you cancel it, what happens? Can you get again dou s ds, right? So same thing. So what I am doing here, multiplying with a dp and dividing with dp. Okay, once again, next plus. Two functions are there. So by keeping plus, dou s by dou t and dou t dt. Again if you cancel it, dou s we get. So dou s and dou s equal again. But here two functions are there. One is p, other one is t. But in this function no t is present, so that means understand that t is constant. In this function no p is present, so that is why understand that is a p is constant. Like this you have to do this equation. Now substituting equation 3 in equation 2, so that means in the place of ds. Okay, so t into, so this is a total, t into total, so total plus vdp written as this. And now multiply t value inside. Yes, t here and here also t, and this t multiply here. So you don't multiply inside, keep it like this only, but here multiply here. So this becomes tds. So it is as it is copy paste. And this tds can be written as what? Tds is t dou s is dou q. So here we can replace t dou s by dou q. Okay, and to this apply Maxwell relation. Which relation? S by p is v by t. It is a Maxwell fourth relation. So if you want to know the drive, please draw the logic box. That is a p s t v. What is there? S by p, s by p, then v by t we get, right? So this is fourth equation. Fourth equation and first equation are always minus, so this minus term has come. Okay, now it is, and this is what it is called cp, right? Cp is equals to dou q by dou t at constant p. So that is why this is changed like this, cp dt. It is t. And now for this, keep these two terms this side and bring remaining these two times that side. It is minus. If you bring this side plus, it is plus. If you bring this side minus. Now see. Okay, now, and now what is see here, dp, you have dp, Can we take common? That is, yes, we can take common. Now bring this dp this side and write a d as dou t by dou p. If you bring this side, it comes in denominator, dou t by dou p into cp at constant h. It is in beginning only we have, and cp bring this side, it is comes like this in denominator, it is multiplying, this side divides. So this is called Joule Thomson or Joule Kelvin effect equation. And this dou t by dou p at constant is called coefficient of Joule Kelvin equation, and sometimes it is denoted by mu also. So right, dou t by dou p at constant h. So sometimes it is denoted by what, mu also, but I didn't explain here mu. So it is a coefficient of Joule Kelvin effect. Now if this term is positive, this is called cooling effect. If this term is negative, is called heating effect. If this term is zero, this term is zero. If a dou p by dou t is zero, there is a neither cooling nor heating. Corresponding temperature is called inversion temperature. Now let me apply, this is for van der Waals equation and ideal gas equation. Okay, if you apply it to the ideal gas and van der Waals equation, then that is over. Now first let me apply to the ideal gas or perfect gas equation for 1 mole. So for perfect gas equation, for 1 mole of gas is PV is equals to RT. And see here what we have to do, dou V by dou T at P. So we have to differentiate this equation with respect to T at constant P, that is. Okay, so before that what you have to write, first write it is V is equals to, yes, written differentiating equation with respect to T at constant P, dou V by dou T, dou V by dou T, and R and P both are constant. Why? Because here written already constant. Then T only differentiable, T value with respect to T it's 1, so it becomes R by P, R by P. Now substitute this R by P value in this equation here. Okay, again that equation is taken here in this place, R by P, and it we write TR by P. TR is what? TR or RT, what? PV. So TR in the place of TR or RT, we write PV. So now this P cancel, V minus V is what? 0. So for ideal gas equation, Joule-Kelvin effect or coefficient of Joule-Kelvin is 0. For ideal gas equation only it is 0. What about for Joule-Kelvin effect for van der Waals equation? Let me explain. Van der Waals equation is this one, P plus A by V square into V minus B is equals to RT. Now differentiating above equation with respect to T at constant pressure. Why do we have to differentiate at constant pressure? See, this is it equation. So V by T at P. So we have to differentiate van der Waals equation with respect to T at constant P. So to this equation, differentiate with the T at constant P. Yes, P constant means 0. It is what? Minus 2A by V cube. Why? Because it is 1 by x square form. 1 by x square, what is the equation differentiation? Minus 2 by x cube. Same thing, minus 2 by x cube. Again to this, again we have to do. Why? Because it is not a T, it is V, that is why dou V by dou T at constant P is equals to. And before that what do we have to do, so before direct doing it, first we have to bring this side. We have to write first here like this, P plus A by V square into is equals to RT by what? V minus B. This thing we have to do first, and it is, see, it is in the form of U by V method. What is U by V method? V U dash minus U V dash by V square. So this is V value, it is total U value. So first V square and write V as it is. Okay, this V is written as it is, and RT is what? RT is U. So its a differentiation is what? Simply R. Why? Because we are differentiating with respect to T. So T value is 1, then R. And now RT, so U as it is and V differentiable. RT as it is, V differentiable means V minus B is a differentiable. So b constant, we write d dou v by dou t at constant p. Now separate them like this. So this by this mean then these two gets cancelled, one thing will remains, and here whole by this one only. And now bring this term is this side. Now it is minus, it will bring this side, it become plus. Yes, and common factor is this bracket only. Take common, yes, taken. And it is right this side and it is right this side. Why? Because the minus term we have to write here, and plus term first is equals to r by v minus v. Yes. Now bring this whole term this side. So it comes in numerator. Already there is a numerator term. So it comes with multiplication this side. Right. Okay. Now multiply v minus b inside. Yes. It comes here and also here. So here v minus b, 1 v minus b gets cancelled. Okay. But here v minus b. Now what we have to do, it cancel, and here 1 v minus b, here v minus b. What I am doing here, I am multiplying v minus b and dividing. So v minus b multiplying, dividing. So now in denominator, see, here v minus b we have, here v minus b we have. So take out 1 by v minus b outside. Okay, so now v minus b, v minus b, v minus b whole square, and here v minus b and this v minus b taken outside, 1 by. Okay, now this already 1 by is there, and its reciprocal goes upside. Am I right? 1 by is there, it goes reciprocal and multiplied with r. So r into v minus v. Okay, now in denominator rt is there here. Why? Because already v minus b is taken outside. So here it is not, it cannot present. Okay, it cannot present. Why? Because 1 by v minus b is taken, it cannot present. Here only rt present. rt present. Am I right? Already these two cancel. 1 by v minus b you have to take, already taken, only rt present here. Okay, rt present. 2a v minus b, here v minus b whole square, and it is taken outside here. Okay, so this is now. Okay, here not present this one, so that is why it is cancelled. Now it goes upside and multiplied with r. Yes, multiplied. Next, v minus b whole square means a minus b whole square, a square minus a square plus b square, and also multiply 2a inside. Already 2a here multiplied, here and here everywhere multiplied. B square plus b square minus 2ab form, it is minus 2ab form. And this constant neglected here. Why here? Neglecting not only b square, and 2vb also neglected. So 2vb here we have. So this whole term is neglected, and this term is also. These two terms are neglected here. Comparison with v square from above equation, and remaining what, 2v square, 2a v square by v cube is remains. Now it is like this. Now square, one square cancel, one more v is present here. Okay, so then r into v minus b by rt minus 2a by v. Now common take outside what, on either side, see, multiplying with t on both sides. So both side t is multiplied, t into, so here t. Now take common outside here in denominator, here take outside, rt take out. So rt, here no rt is, that is why rt right here, and rt cancel. Okay, and this is a bring upside. Already v minus b is there, v minus b, bring is upside, it become like this. Now apply binomial expansion. It is binomial expansion, right? Binomial expansion. And after doing my binomial expansion, multiply this term inside, whole bracket. So this bracket into 1 as it is only, this bracket into this one only. Now separate it. 2a by rtv, 2av by rtv minus 2ab by rtv. So multiply it and separate it. So multiplied and separated. And here more constants present, 2v, 2a, b, r. So more constant present, so that is why it is neglected. Neglecting 2ab by rtv terms from the above equation, and the remaining equations are this only. And now bring v this side. Now it is plus. If you bring this side, it becomes minus. First write plus term and next write minus term. Okay, 2a by rt minus what, v. So sorry, here one thing we have forgotten. Here v is there, I have forgotten v. No v. Here v cancel. No v. Sorry, no v. 2a by rt only. Okay, v cancel. Now v is brought this side, then 2a by rt minus b, right? So this is what it is, the equation already where. So substituting this equation in the equation 4, so it is fourth equation actually. Where, see here, fourth equation. See here again, I have written here fourth equation. And let me see back, where is that fourth equation? See, this is a fourth equation. 1 by cp t into dou v by dou t at constant p, minus v. So it is fourth equation. And again I have taken fourth equation, no need to go back again and again. So that is why here taken. And in this whole place, what, 2a by rt minus b, we have to substitute. Yes, substituted. 1 by cp as it is copy pasted. So this is the equation of van der Waal gas equation. When we applied van der Waal gas equation to the Joule-Kelvin effect, and we got the equation as dou T by dou P at constant enthalpy is equals to 1 by Cp 2A by RT minus B. Now conditions: if 2A by RT is B, so in this place if you keep B, what happens? B minus B becomes 0, right? Whole time is 0, that means is equals to 0. That is, gas on passing through the porous plug suffers neither cooling nor heating when this time is B. Then this corresponding temperature is called inversion temperature. Already explained you. The corresponding temperature is called inversion temperature, and it is expressed by Ti. So 2A by RT I is equals to B. From this, bring this to this side, and this side, Ti is equals to 2A by Br or RB. So this is the final, and no need to write up to here. So just write up to this one only. Okay friends, thank you. Don't forgetting watching this video till end.